Good morning, everyone, and welcome to the C&E Sales Monthly Webinar Series. I'm Jeff Butler, the Technical Manager here. Today's webinar is titled Integrating Fluid Power into Safety Functions. And our presenter today is Heinz Knackstedt. Heinz is a safety specialist here at C&E. He holds a BSEE from the University of Cincinnati. He's a TUV functional safety engineer, and he sits on various safety committees. We've been privileged to have Heinz here at C&E for the past 25 years. Just a few housekeeping items before we start. If you have questions during the webinar, please submit them using the control panel tool on the right side of your screen, and we'll address them at the end of the session. If you don't see that tool, click on the red horizontal arrow, and it should open up the dashboard there where you can see where you could enter questions. And everyone who's registered for this webinar will receive a link to the recording. So if you can't take notes or are feverishly trying to take notes, you'll get a copy that you can look at your leisure later on. And also, please be sure to attend next month's webinar, which is going to be hosted by Brad Hart of C&E. His topic will be interfacing Siemens HMI panels with Allen Bradley PLCs. That webinar will be on December 14th at 10:30. I'll now turn today's webinar over to Heinz.
Good morning, everyone. Again, this is Heinz Knackstedt. I will be putting on some slides that some of you may have seen in previous presentation or in some of the presentations we have done at the expos that we do annually. This is to make sure that we're all on the same page and starting at the same point in the discussion. Today's emphasis will be on safety functions and specifically on the introduction of fluid power. Hydraulic and pneumatic cylinders are still one of the primary sources of motion in the industry, and one of the leading causes of injuries is the uncontrolled rapid motion, especially of pneumatic cylinders, when clearing jams because the pressure has not been correctly relieved and or the flow blocked. To assure that the safety functions have a reliable operation and they do what we expect, we need to understand not only their failure modes, but also how those devices work under different conditions of power. We will be using ISO 13849 as a design guide. Lest anyone get too nervous, we will not be doing any of the math. So this will be purely a high-level verbal discussion of that standard as it would apply to the safety functions. We'll also cover some of the softer issues which involve the selection of the safety functions. And the point here is to assure that the function is the right performance, the right thing for us to do before we worry about implementing it correctly. I've seen a number of correctly implemented functions, but the functions were not adequate or were not correct for the task. We will want to identify the various risk reduction methods and how they can be applied to just about any machine, tool, or assembly machine. And again, we will be including the fluid power aspects. Just a quick reminder that the circuits that we'll be showing are suggested only and are not necessarily applicable to any specific application. So you're certainly free to use them, but be careful that that is indeed the function that you want. Additionally, make sure that you understand the functionality of the devices and follow the manufacturer's directions, both in the application, assembly, and use. And as always, compliance, the federal, state, and local requirements are something that you each individually have to address. A couple quick references that you might want to consider is B11.0, B11.19, and B11.26. All three of these are currently in review for update. B0 and B11.26 should be out yet this year or very early next year. 19, maybe mid-quarter to the end of the quarter of next year. We've done a major reorganization of that particular standard, and it's taken a little longer than we had hoped to put it all back together. Again, as an introduction, obviously machine safety is not an option. OSHA requirement is that as an employer, we provide our employees with a safe place of employment. Consensus standards help us identify the kinds of tasks that are being done, as well as the risk reduction measures which are acceptable, so that the risk that is attained will be acceptable to the organization. A little bit about consensus standards. They basically try to highlight the current state of the art and best practices that the experts in that particular piece of equipment or a particular machine that is being have its standard written are available. Two things that the standards do is that in the OSHA General Duty Clause citation, there are two elements of proof that the consensus standards may provide. One is that the hazard is known in the industry and that a means of remediation exists. OSHA may use these consensus standards as proof that if the hazard was not remediated to an acceptable risk level, they may use the consensus standard as a reference to prove that there was a methodology to do so. Okay, let's go ahead and talk about the getting to an acceptable risk level. The risk assessment is always the first step in a risk reduction process. But just for a moment, let's take a look at some of the realities from the production floor. There are a lot of instances where the safeguarding measures which have been employed have been circumvented or bypassed by the operator. It is one of the leading causes of this is that the operators do what I call a value analysis. They take a look at their perception of the risk and its resultant reduction versus the effort to use the risk reduction measure. If they, in their perception, the value of using the risk reduction measure is not offset by the effort to use it, they will tend not to use it. You have only to look at your company policy in terms of safety glasses and ear protection to understand that logic. There was a study done which indicated what influences safety behavior. It's a matter of perception that we just talked about, habit. I've always done it this way. I'm comfortable. One of the main reasons that we like to suggest that the safeguard and methodologies be installed with the equipment and not added later so you don't have to fight that habit issue. And then there are obstacles that makes the safeguard makes it more difficult for me to perform some task. And in some cases, even barriers, the safeguard prevents me from performing such a task. These are some things that as designers, we need to understand and work on. So what is a good design in terms of intent, in terms of what I'm trying to accomplish, is that I have to have the idea and the perception of the operators in mind so that they will be comfortable using it and they will not end up bypassing it. There were some questionnaires done here a while back. Most of these come from, well, this one came from Schmersel, as a matter of fact, where they asked folks, for what functions do you typically bypass or have to bypass a risk reduction measure? Wouldn't be at all surprised about the troubleshooting of the machine, but I find it interesting that 143 responses were, I have to bypass the safeguards in automatic mode. Similarly for manual setup, material removal, and so on. That suggests that the design of the safeguarding measures was not well thought through. Another very handy tool is to take a look at your design or at your machines, review some of the tasks that the individuals do in the various modes that they have, automatic, setup, manual, and so on, and then see whether there is any advantage in bypassing that in order to make their job easier. There's a list of potential advantages on that diagonal line. If you review a machine that you're designing or is indeed in place, and you find that you have a number of substantial advantages in the ease of doing a job with the safeguards bypassed, I'm rather sure that you will find that bypassing is a norm. Another review that was done was investigation of injuries that occurred when there were indeed safety function safeguards in place, and an attempt to understand the root cause of that. 44% of the injuries were represented by a system where the specification did not correctly identify what it was that was the hazard and how it should be remediated. 15%, the design didn't do what the specification said. 6% of them, the installation was not right. In other words, while the specification and the design was adequate, the installation did not follow those rules. So we'd say, well, there's 65% of the injuries already under control of the designer. What about this green 20%? Well, I would argue that since that is modifications typically by the operators of the system after installation, that as designers, we have control of 85% of the root cause of those injuries in that particular example. Only 15% then are a function of failures, repair, and so on. So again, only 15% are those that come from the operation itself. I'd also like for you to consider a paradigm shift. In my opinion, no plant has not recently had an accident. An accident is any unplanned or unexpected and typically unwanted event. It does not necessarily result in an injury. We frequently call these incidences, also known as near misses and close calls. The point is that there are between 7 to 9 close calls for every one injury, which means we've had quite a number of opportunities to recognize the risk and remediate it, but we waited until the actual injury occurred. The point is that just because I had a close call today doesn't mean it'll be a close call tomorrow, because some of the things that made it a close call today may not be present in the same measure to prevent my injury tomorrow. So, having sort of set the soft issues, let's take a look at the risk reduction process. First, you need a risk assessment team, and typically made up of engineering, HRM folks, but the two most important entities in that team are the operators and the maintenance personnel. They're the ones that know what really goes on. They're also well aware of the close calls and near misses, and they are, after all, the people that have to do the job. The task then is to identify the various tasks that are done in and around that machine, as well as the hazards that that machine or that process represents. We then pair these together and said, for any particular task, these are the hazards that the individual performing that task will be exposed to. When we do the risk assessment now, and we estimate the level of risk of each of these task hazards pairs, if we're doing it on a piece of equipment that already exists, we want to mentally remove all of the risk reduction measures. This is so that we don't forget to review some of those. If in the end of the risk assessment we feel that the remediation was correct, then we would leave it as is. If we find a shortfall, then we obviously would change it. Another thing to remember is that training of individual may not be used in the initial evaluation of the risk. This is because Not everyone may have the same level of training, and therefore the risk for those individuals would vary. You may use training as a risk reduction measure after the fact, after the other risk reduction measures have been applied, but those should be done under control, identified, and recorded as to the training that the people have received. Okay, we now need to understand what the level of risk is. Generally, that is a combination of the level of injury that is most reasonably going to occur and the probability of the occurrence of that harm. There are quite a number of different risk assessment tools that are out there in the world, both manual and computer aided. Any system that your company feels comfortable with is as good as any other. It's just that you want to come up with a consistent process that you, the people that are going to use it, and your management team can be comfortable with. So after we identify the levels of risk, we evaluate each task hazard pair and say, is this level of risk as it stands acceptable? If not, then we identify as part of the risk assessment what level of risk reduction is required and how we're going to do that in order to achieve that acceptable risk. If the risk is sufficiently low that no additional measures are required, then you would leave the machine as is, although typically you'll find that even with a low risk level innately in the machine, there's a good idea to have some procedures and training just so people understand what the risks are and how they are being controlled. If it is up to you now based on, or the team that has identified there are unacceptable risks, the next move is to come up with a hazard control strategy. How are we going to get that risk down to an acceptable level? We use what is called the risk reduction hierarchy, and that is just a series of activities in descending order of effectiveness that we want to review. The first question we would ask, or the first thing we want to try to do, can we eliminate the hazard? Can we do substitution or elimination, use a different process, automate it, use a less corrosive fluid to do the job, etc. If we can't eliminate it, can we reduce the risk? And that is often by making mechanical changes, such as reducing the force, the speed, the frequency with which people need to access the potential hazard, and so on. It is important that this risk assessment be done during the design phase, if at all possible, because this is where you have the most opportunity to affect a positive change. If the design modifications don't get you where you need to go, then we go to what we call engineered risk reduction measures. These are typically fixed covers and guards, or such items as a related control system, what we call safety-related parts of the control system, where we use control devices, relays, push buttons, valves, contactors, and so on, in order to separate, if you will, the operator from the hazard. Typically, these would be interlock guards, safeguarding devices, and so on. The least effective of those, once we have exhausted everything we can do with functional safety and controls, are the administrative controls, where we attempt to keep people safe by saying this is the way you need to do the job, and or personal protective equipment. Recognize, however, that some tasks, some task hazard combinations are inherently risky, have an inherent risk in them, and sometimes safe work practices and procedures are the only process that we can use. Take, for example, handling hot billets. Safety light curtains won't do a whole lot for you when you're exposed to a high latent risk and heat. Okay, talking a little bit about the functional safety. If nothing ever failed, then any safety circuit requirement which could eliminate the hazard would be acceptable. But unfortunately, that's not the case. Hope is not a safety strategy. We need to plan and expect failures and design our circuits accordingly. Excuse me, I just need to back up. There we go. Sorry about it. This is a chart that is available in a number of the different standards that uses some of the same variables you used in assessing the risk to identify the type of circuit that might be acceptable for risk reduction. It again takes a look at the severity of the most reasonable injury, the frequency of exposure, the probability to avoid getting hurt, and that also carries with it the question of how probable is it that the hazard will be there at that particular time. Some hazards are not omnipresent, but are present only under certain circumstances. This then gives you a general direction of the type of performance you should have in your circuit. Okay, after the risk assessment process has identified the measure by which we're going to reduce the risk, we need to verify that that solution will indeed meet the requirement and is acceptable. Needs to be sustainable and meet the operational needs, i.e. it's something that you can use and will be used. Excuse me. There is usually some residual risk, and we have to take a look at what level that is. If we did a redesign, we do a risk assessment, just like we did before, on the new design. And if the new design has an acceptable risk level, we're done. If the new design does not achieve that level of risk reduction, then we need to continue that process. If we used a functional safety performance that defines how the circuit should work and what its reliability needs to be, if the circuit we propose meets the requirement that was set in the risk assessment, then when it is correctly implemented and validated, then that level of risk is assumed to be acceptable. Recognize also that you may be introducing a new risk based on the risk reduction measure that you might be applying. Typical example might be, and this is one that happened to me personally, we changed the source of a MIG welder wiring spool. Instead of a 50-pound, we introduced a 200 to prevent the guy from having to lift the wire and string it so often. We're all very happy until we looked at the layout and found that in order to deliver this 200-pound spool of wire that was going to be on the floor of payoff, had to be lifted by forklift past a long aisle which had no traffic allowances because it opened to offices. So there was a case where our solution probably increased or would have increased the probability of injury, although from a brand new cause. So, again, if the safety function fails the danger, then the risk level reverts back to its original value. Take, for example, a task that is being performed within the reach of a vicious dog. That risk is unacceptable, so the owner perhaps puts up a control measure such as a fence, and you take a look at the fence, you say, yeah, that is adequate, and I accept the level of risk that is there now. And that is on the assumption that the fence is appropriate for the application, right? That it will contain the dog and that it will consistently reduce the risk, i.e. it will not fail to perform its intended function, i.e. it will not fail to danger. If that fence were to fail, the risk is right back to what it was. The dog has not been changed. And this is the same thing when we add functional safety, is we're controlling the access, if you will, or the level of the risk, but we have not changed the actual device itself. So this is something to keep in mind, and why the understanding of the failure mode is so important to us. Okay, so the backbone of safety circuit design is primarily to eliminate or reduce the risk. To do that with safety control systems, we have to manage the failures to danger. I will keep saying failures to danger because some failures I can accept because they do not lead to an increase in risk, whereas other failures do. The example, for example, might be that a contactor dropping out on an application where the contactor drives a motor, the failure to energize the contactor would not be considered a failure to danger. Failing to drop out would. Conversely, if you were designing sump pumps on a submarine, you may want to default to the pump running rather than not running. Failure to run would be a failure to danger in that case. So you need to understand what those failures mean. So the performance level or the reliability of the safety function is based on two issues. One is how quickly in the application do the components and subsystems fail to danger, and what is the probability of, with that failure, that the entire system fails to danger. In some cases, it will definitely fail to danger. In other cases, it won't, and that's part of our design challenge. Need to remember that fluid power devices are included in the failure analysis. I've seen another application where the controls people have said, well, no, we don't do the fluid power. That's somebody else's job. It is very definitely the safety-related parts of the control system don't end at the end of the copper wire. They go all the way to the control of the hazardous device, cylinder, motor, whatever that might be. Another point to remember is that the fluid power device performance and mean time to failure is directly related to the maintenance of the fluid power fluid. If the manufacturer requirements of the fluid quality are not met, there will be a negative impact certainly on the durability and the mean time to failure of those components. A couple quick terms that we throw around quite a bit: mean time to dangerous failure. That is the interval at which the device is expected to fail at a certain percentage. The way this is calculated is the manufacturer does a test of multiple devices, and when 10% of those devices have either failed or failed to danger, in our case, we'd like to have it fail to danger, so we understand what that mechanism is, then those number of cycles are used in a calculation that converts the number of cycles that it takes to reach 10 times that value. How long does it take to reach that number of cycles in our application? The probability of failure to danger per hour, PFH sub D, is a statistical number which defines the probability of failure to danger of a system. It is based on the mean time to failure of the components, individual or in individual channels, and the circuit's ability to safely shut down the hazard if that failure occurs, usually by some system of detection of that failure. Also, the robustness of what we call common cause failure modes, so that the one failure doesn't affect both the safeguarding function itself as well as the ability of that function to detect the failure. For example, common cause failure might be mounting two limit switches on the same subplate. If that subplate falls, neither limit switch is functional. One lies, the other swears to it. You can't detect the fact that that limit switch is no longer functional because they both have sustained the same failure. This is just a chart to give you some idea of the relationship between a percentage of failures over a given period of use for given devices or circuits that have known mean time to dangerous failure. The one thing that I want to make clear is that mean time to dangerous failure is not when the first failure occurs, but is a statistical value that says if I run my system to the mean time to dangerous failure, or for the period of time indicated between failures of the failure per hour, then I will have had a 63% chance of having a failure. You notice here that with a 3-year mean time to dangerous failure, I'm at 63. If I have a mean time to failure of, say, 30, notice that at 30 years, I still have 63%, but with the 3-year use, I would have here it is the curve. You can read it yourself, only maybe a 4 or 5% probability of failure. So you can see how the mean time to failure and the amount of use, basically how many of those cycles to the failure mode that I consume in that time period, determines what the probability of failure during that time period will be. Okay, so let's get back to reducing the risk. We have designed the unit. We are now going to install it. After we install it, there should be a validation period. This basically says that I'm going to test to see whether the circuit as installed does what the requirements from the risk assessment said. This written validation plan, first of all, should show you how to do the test safely. After all, we don't know yet whether it's going to work or not. So you're going to be careful how you test this. Obviously, you should test or simulate the reasonably foreseen failure modes as well as all of the safety functions that you included. There should be a specific expected result for each test. If you have 2 contactors that are supposed to drop out when you open an interlock door, make sure both drop out, not just one, because that's part of your design. Look for systemic errors, those that are design errors that don't depend on a failure mode, but are inherently there and wait just for the error that we may have designed into it. For that reason, offline simulation, while it's a good tool for designing, is not a good way to validate, because errors and assumptions that I made in the design, I'm very likely to include in my simulation test. I want to make sure you document the results for others to see what happened and how it worked out. Okay, a little bit about 13849 in perspective. I'm going to go through this rather quickly. The main thing is that you do not need to worry about the specifics of 13849 in terms of meeting it, unless you are claiming to adhere to RA 1506, which does have that included, or as in some organizations, your customer or your individual plants have adopted it internally. The calculations that we do can give us some general idea of how well the circuit is going to work, and it also gives me a good idea of if I need to increase the performance, what variables, what things I ought to change, where I get the most bang for my money. The most important feature of 13849 is its discipline if I follow it. A little explanation of how it works. This is the idea of the functional safety. I'm going to talk about the process, how it works. First thing I need is the risk assessment. There are 4 supporting stool legs. That is the category, which is the circuit structure, how the components are installed. The second one is mean time to dangerous failures of the components or the subsystems. The third one is the ability to detect the failure so that I can effect a safe shutdown. The fourth is the common cause failure so that the test is indeed robust. The underpinning of this is the verification that I'm doing what the requirement was from the risk assessment, the validation that it does indeed perform the same way. This is just a verbal description of what we've just discussed here. This all then provides us with a basis for identifying what the level of performance is. They're rated from PLA to PLE. This is a chart that says these are the mean time to dangerous failure, the probability of dangerous failure per hour that I must design to meet any one of these performance levels. Notice that, for example, I have multiple ways of reaching, for instance, a design D level by different categories, different abilities to detect failures, and so on. We'll talk about that in a little bit greater detail. So, how do functional circuits really behave? How do they look? How can we understand how they work and what they do? This is done with what we call a functional safety-related block diagram. It identifies the main components of any one particular safety function in terms of a sensor, some logic, evaluation, if you will, and output. These may be individual components such as limit switches, contactors, or they may be groups of devices, or they may be what we call encapsulated systems, which are complete assemblies in and of themselves. Failure to danger of any one of these blocks results in the loss of the safety function of that particular channel. The question then becomes whether or not that means that the entire system has failed to danger. We'll talk about that in a little bit greater detail in a moment. Remember also the interconnection between these devices. Failure in those could also lead in the loss of the safety function. Rules are very simple. All of the items in a given channel that can lead to the loss of the safety function are shown in series. In other words, in that string like I just showed you. If there are alternate means of performing the same function, such as the dual contactors, which I talked about, then those would be shown in parallel. Do not confuse the electrical and the fluid power flow with the orientation of the safety block function. For example, if I have a manual bypass or a muting module to bypass a door interlock under certain circumstances in manual operation, I would have the contacts of that manual bypass block or manual suspension block logic in parallel with the output of the door interlock monitoring function at the logic level. However, in the fault diagram, the safety-related function block diagram, I would show them in series because a failure of the bypassing or muting function, if it fails to release that function, then I would not have any monitoring of the door. So a failure of that device to drop its muting or suspension function is a failure to danger. Again, a quick review of the components. We have, again, the input, the logic, the output, the hardwire or network interface, remembering that the components in that block diagram could be individual components and or encapsulated subsystems. By the encapsulated subsystems, we mean, for example, safety light curtain, which does its own testing and provides us with a high level of reliability and or monitoring. Could also be a logical function such as safe hold, safe speed on a variable frequency drive. It is also possible that a device may have multiple failure modes. Take, for example, a contactor. It may have a both dry or no load rating and a full load rating. And both of those have to be included in our logic, and we will take a look at that in a minute. PLCs. A block PLC will typically have one measure of reliability, but if you have additional input modules, such as remote I/O, choices, communication modules, and so on and so forth, the failure mode of each of those devices must be identified as well. A little bit on fluid power. Fluid power are a lot different devices because they have certain unique responses that are a function of the device itself. Have the single solenoid spring return, which is a device where when we remove power from the solenoid, the spool shifts back, which means that there is a high possibility that when we drop the solenoid power, that it might initiate a motion. If, for example, the cylinder had been advanced, it would return when we lose that power. Something to remember with the e-stop function. Double solenoid detented valve says that once I have shifted that spool, it will stay in that position until I reverse it, which means that when I power it in the other direction, I get a reversal. But if it is moving and I drop the power to that solenoid valve, that motion will continue. The third type is a spring center. In that case, when I de-energize either one of the two solenoids, I go to a third position called a center position, and that may have different configurations as to what is done at the supply and the load ports. In order to reduce the risk from fluid power devices, typically what we want to do is block the supply to the hazard as well as venting the lines, such as blocking the flow to the cylinder as well as blocking its exhaust. Especially this is true when we have an overhauling load such as the vertical column. We may also want to add some kind of a pilot check or blocking valve so that the cylinder won't move. A quick reminder, there are multiple types of relief valves. If you ever use any with remote control, that both pressure relief valves, which typically vent, and pressure reducing valves, which typically need to have a fluid flow in order to achieve that lower value. I mentioned earlier the problem about air cylinders. Typically, we control the exhaust from that cylinder, which develops a back pressure on an orifice so that the cylinder can only move a certain speed. If there's a jam, that back pressure is vented, and if the pressure to the other side of the cylinder piston and or the exhaust from that piston is not blocked by some other method, if someone reaches in and relieves the jam, there'll be a very high acceleration as that cylinder moves forward. So this is one of the more dangerous things for people to do if there's not an assured control of that airflow. Hydraulics are not quite as bad in that they will only advance at the speed at which they have been set. There are a couple different ways to do that. Typically, we have the meter out. If I meter in, I limit the speed with which the cylinder can ever move. However, unfortunately, if I have high friction and stiction, this results in a rather erratic motion. In that case, we could actually add both a flow in and flow out exhaust. The flow out should be as close to the cylinder as possible to reduce the volume, so that if there is no back pressure due to motion, when that jam is relieved, I can limit the speed at which it can move forward by controlling the inlet flow until the exhaust back pressure takes over. Okay, let's talk a little bit now about the categories. Excuse me. I'm running a skosh a bit late, so I'm going to have to pick up the speed a little bit here. Categories are based on how the units or the components are put together. Category B and 1 are safety-related block diagram, shows them in series. If any one device fails to danger, then the entire system fails to danger. It's a very simple circuit. The only difference between a category B and 1 is the mean time to failure. The fluid power would be very simple. I would have a valve and a control, no monitoring, no parallel paths. Category 2 is still a single channel control. A single failure will still lead to the loss of the safety, but I have some level of monitoring which either warns or perhaps even prevents further cycling of the hazard until the error has been detected. There are relatively few good circuits that do that well. Category 2 is difficult to design and to get your value. The other problem is that if the failure occurs in the monitoring system, then you revert back to either a category 1 or a category B circuit, depending on the mean time to failure of your components. Fluid power application in this case might be that I add a pressure switch and monitor to see whether I vent when I should. Again, good design would mean that you check this pressure switch for operation, at least in the logic, so that you know that it is functioning at that when it shows zero pressure. That's really what it's meant. This is my definition of dual channel. I have seen these kind of applications. You see here, somebody's jammed this particular contactor with 2 screws rather than the single channel 1 screw. Category 3 means that I have 2 different channels by which I can eliminate the hazard, and I have some level of monitoring of one channel and the other. The theory is that when I have a failure in one channel, the other channel will eliminate the hazard, and the monitoring between the 2 channels will prevent further cycling. This is an electrical diagram here. I've got a number of e-stop circuit push buttons here, monitoring the final contactors or whatever it is that's causing the motion, so that if one or the other of those devices were to fail to drop out, I could not restart the process. The case here, what the fluid power might look like, I've got a dump valve here, which is being directly monitored with a direct operating switch. I monitor the second valve indirectly by monitoring the process. And if the machine is running, then I know at least the valve moves. Unfortunately, that is not a guarantee that the unit will spring center. For that, I would have to run some kind of a dynamic test where I halt the motion and then see whether when I thought it should halt, it might end up at one or the other of the end spots. That's done rather intermittently because people don't like to put that much dead time into a circuit. Category 4 looks very much like a category 3, difference being that the that the monitoring is much more robust, and the theory is that if there is a failure that I do not detect, then the circuit must continue to provide dual channel security until a second fault occurs, then I detect that combination. So the theory is that that circuit should reasonably not fail to danger. Here's an electrical circuit, even looking to see whether the contact block fell off. Here is a fluid power where I have 2 valves in series, each one being monitored, which would be monitored here in my safety circuit. It's also possible to buy valves that have volumetric check so that they can detect whether a failure has occurred or not. Okay, Let's move on. This is a diagram of what the safety system might look like. You see here I've got 2 encapsulated units that I can evaluate the performance of the whole system. Here is a fluid power example that we might take a look at. And I have drawn here what the safety-related block diagram should look like. Notice here I have both the mechanical failure and the electrical failure, the contact set, as though they were individual components. K1 is a dual channel, or in its particular case is a safety interface module. And notice I have the 2 valves just like we show in the circuit here. Here's a little bit more complicated version. Again, I have a dual channel control here, and that is taken care of by their internal fault detection mode. Then I have in the hazardous direction either centering of this valve or the blocking of the exhaust of that cylinder in the advanced motion with this pilot operated check. Notice here, if either one of these valves fail, this channel fails, this one is alone. Point to remember, which is very important, notice that if the motion in the other direction were also hazardous, only this valve would go, and the most I could have in the retract motion would be a Cat 2 single channel with monitoring. So it's very important to understand that how the valve is used and what its normal position is, its spring center position, is how the system will actually end up working. Question here, is this a dual channel circuit? And I would take a quick look at it and said, well, yeah, maybe it has 2 valves, right? Valve here, valve here. But if we draw the functional diagram and understand how this thing works, we find that the direction or the power control is under the control only of this directional valve, because V2 has no function, because if the pilot valve is not released, which is a function of the failure of V1, V2 does no work. So power up and power down safety is a single channel. Drift down is a single channel, but notice it has 2 failure modes, V1 and V2. And if I vent the system here, then I can hold that piston up without regard of the functionality of V1, because if the supply line is vented, the pilot will be vented as well. So I will hold that cylinder up with the check valve. Here's another circuit, a little bit minor modifications, similar, except we've added a 3rd valve here. One point that I should make is that these are pilot lines, and a good design on multiple units would have the pilot line go back to tank on a separate line so that a line surge doesn't cause a shift. Functional diagram of this one is what you might expect. Again, power up is a single channel, whereas control of power down is dual channel. Either this valve venting and the check valve closing, or this cylinder, correction, this valve spring centering will cause that cylinder not to advance. Okay? So in this particular case, we have a dual channel for the power down and drift, but only a single channel in the retract mode. This is a circuit which is a little bit more complicated. What we have here is 2 functions that we want to talk about. Remember, we said that one of the ways of controlling the hazard is to perhaps reduce speed. This is an example where we use a 2-way valve and a safety rated speed control. so that perhaps in the manual mode, we bypass the interlock gate, which normally would shut off the hydraulics down here, or my air of the air, this is an air drawing, would close this off to provide the safety. But since I have to move that cylinder in my setup mode, I provide a slow speed so that I increase my ability to escape, reduce my risk in that manner. In addition to that, I have two pilot-operated check valves, which prevent motion. For example, if I do pull out a jam, as long as the valve has spring centered here, these check valves will block any motion. Again, and this is an interesting issue with statistics, if I want to discuss the safety of any motion, I have the potential failure mode of these three valves. If I want to discuss them individually, then the reliability would be a little bit higher because I have only two devices in there instead of three. The argument, of course, would be, well, yes, but is there really any difference between the motion of the two? There might be an issue where the hazard is higher in one direction than the other, and I don't want to include the check valve in the one area in that discussion. This one is probably the most complicated one that you might run into in a safety function. What we have here is a category 4, which is the highest level of performance, where we have two pilot-operated check valves, each one controlled by its own valve. And the diagram for the fluid power only is V1, 2, and 3, which is these two gentlemen here, and V1, V4, which is these here. Now, I can claim a category 3 PLD with this particular design because I can have a 90% probability or percentage of detecting a failure. And it's not any higher than that because I don't have any direct monitoring of this particular valve. I don't know if I'm going to get a failure here. I can't check it against a potential failure here. This particular valve, I have both a pressure switch here on this port and a check valve, and I can do what is called a back check or monitoring and set up a circuit that says anytime I dump this valve, I must also see the appropriate position of this particular valve here and that limit switch. So I can not only assure that the unit is working, but I can be sure that both of these devices are cycling. I don't have that opportunity with this unit unless I add a direct operating limit switch on the spool detection or have the ability to add another pressure switch here and again do the same kind of monitoring. One other thing that I've mentioned briefly that we've got to make sure we manage to do is that the software must be done correctly, should be done with some monitoring by other individuals so that the systematic errors are not left in the circuit. This is the end of my formal presentation. Jeff, if you would take a look for me and see whether we've got any questions that someone might have supplied.
Thank you, Heinz. Nice job. At this point, no questions. Folks, if you have any questions for Heinz, use the question panel over on the right-hand side of the screen. We'll wait a minute or so and see if anybody types any in. We'll also want to just remind you that Heinz is one of 13 specialists here at C&E Sales. Heinz's specialty is safety, machine safeguarding, and we also have automation specialists, motion specialists, vision specialists, And so if you have applications that you're looking at, you need some assistance with just some ideas, that's what these guys do. They get to focus in on their specialty all day, every day. And if you have a machine that you are concerned about safety with, either grab, get hold of your C&E salesperson, or you can contact Heinz directly. And there's another safety specialist here at C&E, Steve Wright, and they can come out, take a look at the machine with you, and kind of go through that process and help you understand what you would need to do to make that machine safe. Heinz, I don't see any questions coming through. So with that, we will conclude the webinar. Thank you very much, and thank you all for attending.